Hope the voice is audible. Screens are visible. Okay, thank you. Will commence soon. First, let us see the list of assignments for the day. Zero 62 will have the class notes assigned. First, we have additional assignments. In this class, we will be using only the KTU register numbers because using roll numbers and base numbers simultaneously make things a little confusing. Okay, let us commence. Good morning. Wearing is 19 here. $32. Okay, we will commence. The others join. Okay, meanwhile, let me copy that attendance list. Okay, so Pumping lemma we have discussed on 2 days. Hope that everything is clear. Voice is audible. Screen is visible. So today we will the discussion on the proof of pumping lemma. We will postpone for the time being. Today we will now discuss some properties of CFLs, that is simplification of CFLs. There we will focus. Okay. That is first about the Chomsky normal form. Chomsky, many of you may be aware that it's an American personality, linguist. So very old, but still alive. Have his own opinion on human rights matters. Linguist is also he's a computer scientist anyway. For us, his contribution the theory of computer science, because the theoretical computer science that we are studying presently is developed at a beginning stage of the digital computers in the 60s, 50s, 60s, 70s, and even the 30s, even before the development of transistors, as mentioned already. Because of its, it is so inherent in mathematics, they are still irrelevant. Okay. Because our compilers and so many other advancements in theoretical side of the computer science development, operating system extra very much rely on these studies. Okay. Now, CFCs that we have been seeing, we have seen so far, even though we haven't seen many, may provide different types of productions. That is the right side of a production could be in many fashion. So to simplify things, now Chomsky suggested a simple form, and we have proved theorem and proof that they will represent a very CFG in whatever form they have already represented, except epsilon. Epsilon is a language anyway, except for epsilon. We want to show that every CFL is generated by a CFG where all productions are of the form. This is the form. So if every production of this normal form, simplified form, every production is of this form, then we will say it is in Chomsky normal form, simply CNF. A variable producing two variables, or a variable producing a single terminal symbol. So every production in multiple, having multiple variables or a combination of strings, variables and terminals could be converted to this fashion. Okay. And the switch off the camera, maybe that will help screen viewability a little better. Okay. Hope everything is fine here. And here, even though in YouTube it will be a little lagged behind. Okay. Okay, maybe continue the discussion. Okay. So for ABC are variables and is a terminal. This is called CNF, and to get there we have to. Okay, the process of converting, simplifying a grammar into CNF, simplified form, involves three processes. One, eliminate useless symbols. For that, we have to define what is a useless symbol. So we will define what is a symbol that is a useful symbol. Okay. What is a useful symbol is defined. Those that do not appear in any derivation. Yes, the start symbol to a string of terminals. If a symbol in a grammar doesn't appear anywhere in a production process, then that symbol may be a terminal symbol, may be a variable. These are the two options. That is treated as a useless symbol. We have to eliminate it. So for this step, one step is eliminate useless symbols. That is those that do not appear in any derivation from S to multiple stages to a string for a start symbol as standard terminal type. Okay. W could be any. If you take all strings, and if there is a variable or simply a symbol which is not at all appearing in any such production, that symbol is maybe variable or a terminal symbol is a useless one. We have to eliminate that to simplify a grammar to CNF form. In a standard form, why we are going for a CNF Chomsky normal form, standard simplified form will help us to process the grammar much more easily, because this CFG is useful in programming language section. Okay. Now eliminate epsilon productions. That is producing productions of the form A derives epsilon. And we have to eliminate epsilon productions. Okay, epsilon productions are these. Okay. We will speak about it because we are speaking about a language which is without epsilon as its member. Okay, somewhere it is written. Okay, we want to show that every CFL without epsilon. Okay, we are not discussing empty language here. Okay, a non-empty language, the all these discussions, simplification extra for a non-empty language. Okay, then eliminate unit productions. That is productions of the form A gives B, where A and B are variables. We have seen such productions in the expressions CFG we have discussed in the class. There we have E gives I extra. Such productions are eliminated. That is called unit productions. One variable generating another variable. Okay. So these are the three stages in converting a grammar into this form. Okay. Eliminate useless symbols, eliminate epsilon productions, eliminate unit productions. First this we will do, and we will get to that. Anyway, first eliminating useless symbols. So we have stated what is a useless symbol. So similarly, its opposite is a useful symbol. Okay, if a symbol X is useful for a grammar, G is equal to VTPS. If there is a derivation S to W, in that stage X appears somewhere, alpha, X, beta. For a terminal string W, alpha could be a subset of terminals and variables. Beta is also okay. String over, let us say alpha and beta are strings over V union T. Okay, simply. Okay. So X is a symbol. It should appear in somewhere. Maybe X, maybe S. It's maybe in the W. Okay. So such a symbol is a useful symbol. Okay. Symbols that are not useful are called useless symbols. Then we have another one is we are eliminating useless symbols. Okay. And then for that we are defining what is called useful symbols. Okay. And then we are categorizing those symbols as generating symbols and reachable symbols. A symbol is further categorizing for this purpose, eliminating useless symbols. A symbol is generating if that is if a symbol is generating if there is a derivation sequence that leads to a string over the terminals. So a symbol X is generating if X derives W for some W belonging to T star. Okay. there should be a sequence from X to W. Okay. A symbol is reachable. Suppose a variable is there, if that variable is ultimately derivation sequence from that variable should lead to a string over. For that matter, every terminal is generated. Okay. A symbol X is reachable. So we are defining reachable symbols now. Generating, we have just mentioned. Now reachable. Reachable from the start. Reachable means if that symbol is there somewhere in the sequence. If a symbol is reachable if S derives alpha X beta for some alpha beta, which is a subset of P union T star. Okay. So alpha X beta. In this case, from start symbol is in the process of multiple derivation sequences, somewhere you encounter an X. Suppose X is a symbol. Okay, it may be variable or it may be a terminal. Okay, so X is reachable if from the start symbol using any of the production sequences, it finally leads to a string where X appears. Then X is a reachable symbol. So if we eliminate non-generating symbols first, and then non-reachable ones, we will be left with only useful symbols. Okay, that is the statement here. That is, to eliminate useless symbols, first we will eliminate non-generating symbols and then non-reachable symbols. Okay, non-reachable generating first and non-reachable next. Generating symbols means there is a derivation sequence from that symbol which leads to a string over terminals. Reachable means from X there is a path to that symbol. Maybe that symbol may not be alone, but it should be there on the right side of a derivation sequence. X should appear, then X is reachable. Okay. Meanwhile, 062 will have the class notes assignments for the day. Okay, additional system. Okay. Now let us consider an example. Let GBS derives gives AB or A gives B two product, rather three productions. S gives AB, S gives A gives B. Suppose now S is generating. S gives A, so S is generating. Okay, A is generating. A gives B. Generating means from that symbol there are three variables here. Okay, three variables here. Well, generating definitely terminals are generating. Okay, so forget about that. We are focusing on variables now. There are three variables S, A, and B. S is generating because S gives A. Okay, A gives B is there. So A is also generating B. B is not on the left side of any derivation sequence, so B is not generating. S and R are generating, so B is not generating. I think maybe a little clear. So what we do, if we eliminate B, we have to eliminate S derives A, B. Since B is not generating, we will eliminate a production involving AB. So we have three productions. S derives AB, S derives A, S A gives B. So S gives AB is eliminated. So what is left is S gives A and A gives B. So that is what is avoided. Now look at this. This is our start symbol. Okay. So S is definitely reachable. So from the start symbol, S is reachable. From S, if you start from S, A is not at all reachable. So A is non-reachable. In this case, previously A was reachable, but here, once you eliminate this production, S gives AB, now A is not reachable. So remove that also. Now only S is reachable, eliminate A and B. Since A is gone, the B is also gone. Okay. Along with that, this production is gone. Okay. So A and B. So we are left with S gives A. So this grammar is this CFG is in effect is only the language of A. S gives A. Only that much is there. Even though it is written like this, it will only, whatever you do, it will only produce A's. Okay, so this the language of this CFG is very simple. It is simply reset A, nothing more, nothing less. Okay, so what we have done, repeating once again. First, we have eliminated non-generating symbols. Then we have removed unreachable symbols. On the other hand, if we eliminate non-reachable first, then we may not get this result. We find that all symbols are reachable. If we try to eliminate non-reachable symbols, first we find that all symbols are reachable. So from S, A is reachable, S is reachable, A is reachable, B is reachable. Okay. From S, A is reachable, this small letter is reachable, B is also reachable. Okay, from S, A very simple is reachable. So we then eliminate B as non-generating. Now let us first let us go on to delete non-generating symbols. Okay, B is not generated, S is generating, A is generating, B is not generated. So what we have, we will remove S, produces A, B is removed. So what is left behind is S gives A and A gives. That still contains useless symbols, because A is not reachable here. From S, A is not reachable and B is also not reachable. Okay. So here the process is over. First we have removed non-reachable and we have non-reachable. So that is not the sequence. This is just right from the point that first we have to remove non-generating. Okay. In the other way around, we get a still not fully simplified grammar. Okay. This is what we want. Okay. That is obtained. This is just an example. Anyway, this drives on the point that we have to first remove non-generating and then non-reachable. First G, then R. Okay, in the alphabetical sequence. So easy to remember. First to remove non-generating, then eliminate non-reachable. Okay. Hope it is clear. We will explain once again. Suppose this is the grammar, the simplification process. One thing is eliminate useless symbols. Useless symbols are those symbols which are not reachable and non-generating. Okay, we have discussed it already. So first, non-generating. S is generating, A is generating. From S you will reach S terminal symbol, or from A you will reach S terminal string. So S and A are generated. We will retain the B is not generated. So we will remove B, and B is removed. S derives A, B is gone. So what is left behind is S gives A and A gives B is left behind. Okay. So now we will eliminate unreachable symbols. S is the start symbol, so S is definitely reachable. So this will be there. From S you start, you will reach S string of terminals. No further process there. So A is not reachable from S. From S, whatever you do, you won't see A on the right side. Okay, so A is reachable, so we will remove this. So what is left behind is A, S gives A. So this is the language of S gives means the language is simply a single symbol A. So that is the process. The theorem we will skip for the time being. theorem is that if LG is equal to V, TPS, PSCFG such that LG is not empty, then G1 is V1, T1, P1S. Be the grammar obtained by eliminating all as before, all non-generating symbols and the productions they occur in. Let the new grammar be G2 is equal to V2, T2, P2 is eliminate G from G2 all non-reachable symbols and the production they occur in. So we will get G1 from that. Okay, G is given. First eliminate non-reachable, we will get G2. From that we eliminate, first remove non-generating. G2 will get, from that we will, as before, delete, remove non-reachable, we will get P1. The theorem is that they are equivalent. Okay, the proof is, we are not discussing for the time being. Okay. If time permits, we will come back to discuss if the syllabus wants it. Okay. Now the algorithm. We have to give algorithm to compute the generating and reachable symbols of GVT. This is the algorithm for generating reachable and generating symbols. The generating symbols GG are computed by the following closure algorithm. GG, as mentioned already, GG is equal to T. Okay, this assignment. Okay, this is equal to GG is equal to T. All terminal symbols are generating symbols. That means, what is a generating symbol? We have seen that if a production sequence reaches a string over the terminals. Anyway, by that definition, or in this case, the basis of the definition is that every terminal is a generating symbol. Okay. Now, if alpha belongs to GG and X derives alpha belong to P, then GG is equal to GG union X. What is that? Suppose alpha is in GG, alpha may be a single, alpha is a single symbol, alpha is in GG, generating symbol may be terminal for a variable. Then if and X gives alpha belongs to P, X gives alpha belongs to P. Okay, it is, if such a production is there, then we will add that symbol also. If that symbol also to the generating symbols. GG is GG union X, provided X gives alpha is a member of the productions, where alpha belongs to G of G. We will see that the GBS gives AB, A gives B. The first GG is equal to AB. Okay, generating symbols. All terminals are as per this one. As per this one, first GG is equal to AB. Okay. Since S gives A is there. Okay, A is here. Okay. S gives A is there. Okay. So we will add, since S gives A, we put S in GG. So we have SG is equal to AB. S is also added. Okay. Hope it is clear. Okay, what we have done is, this is the formal process of collecting generating symbols. Basis is every terminal is a generating symbol. So we have a set for that GG generating set of the symbols, set of the grammar G. Okay, every terminal is in that set. So here, if we consider this grammar, the terminal symbols are A, B. So to start with, GG is equal to A, B. Okay, GG, that is the generating symbols of the grammar G for this grammar. Okay, now S gives A. Now, as per this induction rule, if X gives alpha belongs to P, okay, and alpha is in GG, then that is also a member of the GG. That is the set of generating symbols. S gives A is the, and A is here, so S joins GG. And because A gives B is the, A gives B. Okay, and B is already there, so A is also joining there. So we'll have a small letter A, B, capital S and capital A as part of the generated symbols. B is not there. From B, you cannot have any production, so B is not there. Okay. So S belongs to A, we put S in GG, and because A gives B, add a and that's it. Okay. The theorem is that saturation GG contains all and only the generating symbols of G. Okay, that is the statement. Okay. Proof you are again skipping for the time being. Now reachable symbols, we will now define reachable symbols. Reachable symbols of the grammar G is represented as RG is computed by the following clause alike. Okay. Reachable means all symbols that are reachable from S. Okay, we have seen it already, the formal definition. RG is equal to S. The start symbol is there. Then, if variable A belongs to RG and A gives alpha belongs to a product piece of production, then add all symbols in alpha to RG. If A variable A belongs to RG and A gives alpha is a production, that is if a symbol is reachable already and all the right hand side symbols with a reachable symbol on the left hand side will be added to the set of reachable symbols. Okay, that is the meaning of it. If A is already in the reachable set and if then all the symbols on the right hand side of such a symbol A will be added to the set of reachable symbols. Here again we will use this example. S is equal to A, B, A, B. Suppose this S is association, S, R, G, skill, S will is a reachable symbol. Is a reachable symbol based on the first production. Okay, now we will consider S only here from S. A, S to A, B is there, S gives A is there. So we will add A, B, A to the first stage, to the reachable symbols. So it becomes S, A, B, small letter are added to the A, B are added to the reachable set. So S, A, B, small letter A will be there in the reachable set. After first initialization based on the induction definition, the start symbol S is a reachable symbol. Then all symbols that are on the right hand side of production starting S will be added. So here we have S gives A, B, S gives A. So A, B, A are added to the reachable set. So we have R's. Now we have S, A, B, A are there. Yes, we have considered A gives B is there. Okay, based on the second reproduction, we add a B to the RG, and so all symbols are added. A, B, A, small letter A, B is every symbol is added to the reachable set here. Okay, based on the second one, we add a B to RG and that's it. Okay, so the theorem is at the saturation RG contains all and only the reachable symbol. This method, this is a method, this is an algorithm, and every algorithm should have a proof that is that method is correct. Okay, it captures all reachable symbols and it captures only reachable string. So okay, that's the theorem. Okay, we are skipping again the proof part here. Now the next thing is we have taken care of useless symbols. Okay, eliminating epsilon productions. Okay, our language is L minus empty set. Okay, we shall prove that if L is a civil, then L minus set epsilon has a grammar without epsilon productions. So, as part of this process, we are going to eliminate all productions which generate epsilon. So, eliminating epsilon productions is a part of this process of generating CNF. That is what we are attempting here. Variable A is called to be null level. So, we will call such a variable if in multiple stages a variable reaching production epsilon, then we will call a symbol nullable. Say A may be producing some other, say in this case, A may be producing some other variable string, but still A is nullable. If in one sequence is there which produces epsilon. So in the previous case we have A S gives A B. Okay, now it's not. Then S gives A. Okay, it's not that. Okay, if at any multiple stages, if one symbol gives epsilon, then that symbol is nullable. That doesn't mean that all the productions of A are nullable. No such meaning. Okay. Now let A be nullable. We then replace. We can't simply eliminate directly eliminate a nullable symbol. We have some process there. Okay, we are discussing that here. We will then replace a rule like A gives BAD. See, A is nullable. Okay, so we have two options. In this case, A gives BAD, A gives VAD will be retained, and in another productions, A will be replaced with this production epsilon. A is nullable. So the result derivation sequence, multiple derivation steps are involved, even though A gives in multiple stages epsilon. If there is a production is there, we have another production which will eliminate A from here. So we will have A derives BAD, A derives BD, both will be there. And delete any rules with the body epsilon. Finally, if we reach this epsilon production body, we will delete that. These two we cannot delete as such because they are not epsilon bodies. Okay, they will be retained. Then we will compute null set. Nullable of G. That is the set of nullable symbols of grammar G. We TPS as follows. The process of collecting the nullable symbols of the grammar is given here. Okay. Basis is all sets, all symbols which gives a direct A gives epsilon production. They are nullable. Okay. Then if C1, C2, Ck is a subset of Ng, okay, and A gives, rather it should be C1 comma C2 comma C3. Okay, it's not C1, C2 should be, because Ng is a collection of nullable symbols. So if C1 comma C2 comma Ck is a subset of Ng, in other words, all the C1, C2, Ck are nullable symbols. And if suppose A derives C1, C2, Ck is a production, then we will add A to that nullable set. Hope it is clear. Suppose there is a production. A gives C1, C2, Ck. Okay, that is a production. Okay, and every C1, C2, Ck is a member of the nullable set already. Okay, for all we write for all Ci belonging to Ng. Okay, this is C1 comma C2 repeating. Then if that is the case, then we will add A to the nullable set. Okay, so our purpose here is to eliminate epsilon productions. For that we are actually collecting um, it's, we are collecting uh, symbols which are nullable. A symbol is nullable if there is a production sequence which leads to a null symbol. We can't directly again eliminate a nullable symbol because that may be generating other symbols as well. Okay. Anyway, here we are collecting the null symbols. Anyway, this is a theorem. At saturation, Ng contains all and only the nullable symbols of G again. It's a theorem and it's proof because we have an algorithm. Every time in computer science, we should know that if there is an algorithm, that algorithm should have a theoretical support. Okay, only it is that algorithm is stated as a theorem and it is proved. Such algorithms are accepted. Like anyway, all algorithms that we are discussing, learning, sorting algorithms or searching algorithms, such algorithms have a theoretical backing. Okay, that is correct. It will do the work that properly supported by logical and mathematical arguments. Okay, here this process which we have described will collect all nullable symbols and also it will collect only nullable symbols. Okay, that is this theorem states. Okay, the proof we are again skipping. Anyway, after this stage, we will have we will be able to collect all nullable symbols. Now, once we have collected the nullable symbols, okay, we are collecting these nullable symbols as part of a process described somewhere. Which was that? Okay. So, eliminate all non-generating symbols and then production they occur. Let the eliminate non-reachable symbols. Okay, as part of that we have done the process of okay, that we have completed. Okay, that part we have completed. Then we have we were removing epsilon productions. We have demonstrated eliminating epsilon productions. Okay. So this is what we have commenced this discussion. Sorry, eliminating epsilon production. That is, as part of that, we have collected the nullable symbols. That is, symbols that generates epsilon, null symbol, empty symbol. Once the nullable symbols, we can transform G into G1 as follows. Okay. For each A gives x1, x2, extra belonging to P with n less than or equal to K, nullable symbols, replace it by 2 raised to m holds 1 with each symbol, each sublist of the nullable symbol absent. Okay. The process is we create multiple projections from this. For each x1 to xk belonging to P with n less than or equal to K, nullable symbols say of this is a for it. Suppose this is a projection. This is suppose a projection, and there are K symbols in it. Suppose, and m of them are nullable symbols. Then replace it by sublist of the nullable symbols. In each one, we will remove one symbol, and we will retain in one. We will retain that symbol. Okay, that is the process. One with the suppose x1 is a nullable symbol. We will create one with the x1. We retain the other with the x1 absent. Two options. 2 into x2. 2 into 2 into 2. Suppose there are m such nullable symbols in the sequence, m less than or equal to k, 2 into 2 into 2 raised to m, productions will be generated. We will, so the A gives this, we will replace it by 2 raised to n such numbers. Okay. If m is equal to k, we don't delete all m number symbols. Okay, what is that? Exception. Okay, there is an exception. If m is equal to k, we don't delete all m nullable symbol. If m is equal to k means everything is there. Okay, in that case, if you delete everything, a gives epsilon will be there. That case, we will skip. Okay, there's an exception only, and all the variables are null symbols. So, otherwise, generally the method is it will generate 2 raised to m rows. So once again, what is happening is if x1 is nullable, we will create as before. We have seen it somewhere. We have seen it. A gives BAD. Okay. So for this, A is nullable. Okay. In that case, what we have done is we have BAD is retained. So we have A gives BAD is created. A is nullable. So A is eliminated. So we go to BAD. Similarly, for each nullable symbol, we get two productions. So in this case, there are k symbols of which m which is less than or equal to k. Okay, m symbols are nullable. That means for each one or each of that nullable symbol, we will create one production with that nullable symbol retained, and another production with that nullable symbol obtained, removed. Okay, so we'll have for example, for x1 we will get 2 results. For x2, if it is a nullable, we will get 2 more. So 2 into 2, 4 like that. 2 raised to m folds will be generated. Except for the case if m is equal to k, that means if all the symbols are nullable, we will won't create one particular case. We won't create, that is, if every symbol will be emptied, means a gives epsilon will be generated. That we will not retain. That's only an exception. All other cases. Now finally, that case, we finally this after this process delete all rows of the form A gives epsilon. If this process in this stage also that you cannot be seen, we will remove such productions. So here is the example. Immediately we will finish after this. Let's see, B A gives A, B A gives A, epsilon, B gives B, B epsilon. Ng is equal to, that is, nullable symbols. What's up? They, A gives epsilon, so A is, B gives epsilon, so it is null. Then which is the next one? S gives AB. A is nullable, B is null. So that is also an option. S gives B will be one option, and B is replaced by epsilon, then S gives null. So in 2 stages. A is A and B are nullable directly. S is nullable in the second stage. Okay, in 2 of those steps. Okay. So S, A, B all are nullable symbols. That doesn't mean that S will produce only null string. Okay, no. S will produce null string. That's why it is nullable. S will produce other strings as well. So the first rule is S gives A, B. Okay, it is there. It is there. Now, since A is nullable, we will nullify it. Okay, so we'll have S gives B. Then B is nullable, so we'll remove it. So from we'll complete the discussion. Okay, A, B, S. The first rule will come. S gives A, B. Okay, then the second is A gives A. It is there. Since A is nullable, so we'll have A. And again, the second A is replaced, so you'll have one more A. Then both A's are nullified, so you'll have A gives. And the third, you'll have B gives BB as such. BB, the first one is nullified, the second one is null, and both are null. It's 2 stages we will get it. So these productions we will get it. And okay, further we will discuss next week. Okay. We'll stop the process here. Okay, that's all. Thank you. We will stop the process here. Okay.